This lesson is on section 9.1 titled Sequences. So there's first two vocabulary words that I want you to understand before we go ahead into our examples. The first one is sequence, and all what a sequence is an ordered list of numbers. You've probably seen sequences before in the past, but we're going to be covering them more in depth in this lesson. And then specifically an arithmetic sequence. It's just a fancy word that means the difference between any two consecutive terms is the same. So, for example, an arithmetic sequence is something like this: 3, 5, 7, 9, 11. Are you seeing a pattern in here? If you see a pattern, that's really what an arithmetic sequence is. So when there's a common difference between the numbers, or the difference between the numbers are the same. So if we go from 3 to 5, the difference is 2, so we're kind of like adding 2. So the difference between 5 to 7, 5 plus 2 is 7, 7 plus 2 is 9, and 9 plus 2 is 11. So if you notice, this is a common difference, and the difference between them is the same. So that's why it's an arithmetic sequence. Let's say, for example, this next number was 15. Well, I can say, well, the difference between 11 and 15 is 4. So because of that, that wouldn't make it an arithmetic sequence if I were to add the number 15. But I just wanted to give you a counterexample in that situation. Okay, so let's move on. So our first example says, state whether the sequences are arithmetic. If it is, state the common difference and write the next three terms. Okay, so you first have to see if it's arithmetic or not. So first, let's see if there's a common difference. So we go from 17 to 12. Well, 17 minus 12 is going to be, so we're like going down 5. Okay, the difference is negative 5. So between 12 and 7, again, that difference is, we're going down 5. And then from 7 to 2, yep, we're going down 5 there. And from 2 to negative 3, yep, we're going down 5 there. So we can say yes, it is. And then we want to state the next three terms. Okay, so I'm just going to erase this to give myself room. So if I'm at negative 3 and I go down 5, I'm going to be at negative 8. So that'll be the next term. And then if I'm at negative 8 and I go down 5 again, I'm going to be at negative 13. I'm just subtracting 5. And then if I go from negative 13 and I go down 5, I'm going to be a negative 18. So again, that difference, it should be a negative 5 every time. I'm going down 5. Okay, so I'll circle that answer there. Okay, so let's do the same thing for B. First we have to see if it's arithmetic or not. So from negative 4 to negative 8, looks like I'm going down 4. From negative 8 to negative 16, it looks like I'm going down 8. Uh-oh, right away I already see that there's not a common pattern. So I can stop right there and I can say, no, it's not. And because it's not, there's no three terms that I have to write. A lot of kids get this confused and they say, oh, well, negative 4 times 2 is negative 8. Negative 8 times 2 is negative 16. And then negative 16 times 2 is negative 32. Oh, that's got to be. No. It only deals with adding and subtracting. If you find a pattern that deals with multiplication, it's not arithmetic. We're going to learn later that it's called a geometric sequence. So it does not deal with multiplying or dividing, and it always deals with adding or subtracting, that common difference. So my final example says, write an expression that can be used to find the nth term of the sequence of the perimeter of squares. So we have perimeter of square, so the first perimeter is 4, the second perimeter is 8, the third perimeter is 12, and the last one 16, for example. Then write the next three terms. Okay, so the difference between this one than it was the last one is we have to write an expression that can be used to find the next terms in the sequence, or any term in the sequence. So the easiest way for me to do this is to actually write a table. So I'm just going to draw this table here. And I'm going to say, okay, well, I'm going to count my my x values as my term number, and that's going to be considered my n term, and this will make more sense coming up here. And then my y value is going to be the perimeter, or whatever they gave me in the example. In this case, it was the perimeter. They can give you any unit of measure in any of the type of problems here, but in this case, it's perimeter. So let's just fill in the data that we have. So the first term, this is my first term, is 4. My second term is 8. My third term is 12. And my fourth term is 16. Notice where I'm getting these from. Okay. So now I have to see, okay, so what's that common pattern that I'm getting from here? Okay, well, I can see, every time I go, the difference between these numbers here is a difference of 4. Where I'm going up by 4. We can see that. But in this case, because we're looking for that expression there, we're looking at the relationship between the number of terms and with our perimeter. So we're seeing, how do we go from the term to the perimeter? So let's see, how do we go from 1 to 4? Oh, I have to multiply by 4. How do I go from 2 to 8? Oh, I got to multiply by 4. 3 to 12, you noticing this pattern here, and then 4 to 16 times by 4. So to understand that expression, what we have to do is we have to take the nth term, whatever we're getting, and we're going to multiply it by 4. So we're taking 4 times the nth term, and that's going to be that expression that we're going to use for this problem. So now it says, the second part of this problem says, then write the next 3 terms. Okay, so I know, all right, so if I'm going to find 4, 5, 6, and 7, those are the next 3 terms. So I'm going to plug in, 4 times 5 equals 20. 4 times 6 equals 24. And 4 times 7 equals 28. And those would be the final 3 terms of my sequence. So again, just kind of writing a sort of pattern. Writing a table, find that pattern from the nth term to whatever you're solving for, and then plug in your final 3 terms in order to find the last 3 terms of the sequence. And that brings me to the end of this lesson. Thanks for watching.